Hi everyone. Through this class, we are going to study about FIR filter and windowing using a rectangular window and a triangular window. The filters are frequency selective devices. The nature of filtering action is determined by the frequency response characteristics h of e raised to j omega, which in turn depends on the choice of system parameters. Thus, by proper selection of the coefficients, we can design frequency selective filters that pass signals with frequency components in some bands, while they attenuate signals that contain frequency components in other frequency bands. In general, the specification of a digital filter will be design frequency response HD of e raised to j omega. The desired impulse response small hd of n of the digital filter can be obtained by taking inverse Fourier transform of hd of e raised to j omega. H of z of the digital filter is obtained by taking z transform of impulse response. Since hd of n is an infinite duration signal, the transfer function obtained from hd of n will have infinite terms. This cannot be realized or implemented in a digital system. Therefore, finite number of samples of small hd of n are selected to form the impulse response h of n. The transfer function h of z is obtained by taking z transform of finite samples of impulse responses. The filter designed by using finite samples of impulse responses are called FIR or finite impulse response filters. Advantages of FIR filters. First advantage, FIR filters with exactly linear phase can be easily designed. Second one, efficient realizations of FIR filter exist as both recursive and non-recursive structures. Recursive means a system whose output at any time depends on number of past output values as well as present and past input values. Non-recursive means a system whose output at any time depends only on number of present and past input values. Third property, FIR filters realized non-recursively, that is by direct convolution, are always stable. Fourth advantage, a round of noise which is inherent in realizations with present precision arithmetic can easily be made small for non-recursive realization of FIR filters. Disadvantages. First one, the duration of the impulse response should be large. If n is large, then we get sharp cutoff filter. Hence, a large amount of processing is required to realize such filters when realized via slow convolution. Second disadvantage, the delay of linear phase FIR filters need not always be an integer number of samples. This non-integral delay can lead to some problems in digital signal processing. Magnitude response of ideal low pass, high pass, band pass and band stop filters are shown here. The ideal filters are non-causal. That means output of the system at any time depends upon future inputs or future outputs. Hence, they are unrealizable. In ideal case, there is a sharp cutoff from passband to stopband. But in practice, it is not necessary to insist that the magnitude h of e raised to j omega be constant in the entire passband of the filter. A small amount of ripple in passband is usually tolerable. Similarly, it is not necessary for the filter response h of e raised to j omega to be 0 in the stopband. A small amount of ripple in stopband is also tolerable. The transition of the frequency response from passband to stop band, that defines the transition band or transition region of the filter. The passband edge frequency omega p defines the edge of this passband, and this omega s, that is the stop band edge frequency, this denotes the beginning of the stop band. Here we can see that there are ripples in passband and the stop band, and the passband ripple, that is denoted by delta p, and stop band ripple, that is denoted by delta s. When we design a particular filter, we want to specify passband edge frequency omega p, stop band edge frequency omega s, passband ripple delta p, and stop band ripple delta s. The windows are finite duration sequences used to modify the impulse response of the FIR filter. And by using these windows, we can reduce the ripples in passband and stop bands. So, in order to achieve the desired transition from passband to stop band, we can use windows. There are different types of window sequences. They are rectangular window, Bartlett window or triangular window, Hanning window, Hamming window, Blackman window, Kaiser window, etc. First, we consider the rectangular window. The endpoint rectangular window WR of n is defined as WR of n equal to 1, where n equal to minus n minus 1 by 2 to plus n minus 1 by 2, and WR of n equal to 0 for other values of n. Another equation for this WR of n is WR of n equal to 1 when n equal to 0 to n minus 1, and WR of n is 0 for other values of n. We can use this first equation for odd values of n, whereas we can use the second equation for even or odd values of n. If we use this equation for this rectangular window, when n equal to 31, here this minus n minus 1 by 2 is minus 15 and plus n minus 1 by 2 is plus 15. So, if we plot this WR of n versus n, then for minus 15, WR of n corresponding to this n value is 1. For minus 14 also it is 1, minus 13 it is 1, up to this plus 15 we can see that WR of n equal to 1. But in between this minus 15 and minus 14 its value is 0. In between minus 14 and minus 13 its value is 0. So this represents a rectangular window. The frequency response or frequency spectrum of rectangular window WR of e raised to j omega is Fourier transform of the window sequence WR of n. Therefore, it is equal to sigma n equal to minus n minus 1 by 2 to plus n minus 1 by 2 e raised to minus j omega n. Now, change this lower limit as 0. So, for changing this, put n as n minus 1 by 2. So, this is equal to, here lower limit changes into 0. Upper limit it is n minus 1 by 2 minus n minus 1 by 2. That is 2 times n minus 1 divided by 2, or it is n minus 1. That is equal to e raised to minus j omega. Now, n is n minus 1 by 2. So, it is equal to sigma n equal to 0 to n minus 1. Then separate this. So, it is e raised to minus j omega n into e raised to plus n minus 1 by 2 into j omega. That is equal to e raised to minus j omega n minus 1 by 2 into sigma e raised to minus j omega n. Here the limit for the sigma is 0 and n minus 1. And we know that sigma n equal to 0 to n minus 1 c raised to n is 1 minus c raised to n by 1 minus c. So putting this value here it is equal to 1 minus e raised to minus j omega n divided by 1 minus e raised to minus j omega. Then it is equal to this e raised to j omega n minus 1 by 2 into, instead of this 1, we can write it as e raised to minus j omega n by 2 into e raised to plus j omega n by 2. And this e raised to minus j omega n can be written as e raised to minus j omega n by 2 into e raised to minus j omega n by 2. And this 1 here we write it as e raised to minus j omega by 2 into e raised to j omega by 2. This e raised to minus j omega we write it as e raised to minus j omega by 2 into e raised to minus j omega by 2. Then here it is equal to e raised to j omega n by 2 into e raised to j omega into minus 1 by 2, that is e raised to minus j omega by 2. Then this e raised to minus j omega n by 2 common in this equation. So it is in e raised to minus j omega n by 2 into e raised to this j omega n by 2 minus e raised to minus j omega n by 2. That divided by here also e raised to minus j omega by 2 common. So it is e raised to minus j omega by 2 into e raised to j omega by 2 minus e raised to minus j omega by 2. Now we can see that this e raised to minus j omega by 2 in denominator and e raised to minus j omega by 2 in numerator cancels. And this e raised to j omega n by 2 into e raised to minus j omega n by 2, that is 1. Now this is equal to e raised to j omega n by 2 minus e raised to minus j omega n by 2 divided by e raised to j omega by 2 minus e raised to minus j omega by 2. And we know that e raised to j theta minus e raised to minus j theta divided by 2j is sin theta. So here this term that divided by 2j is sin omega n by 2. And this e raised to j omega by 2 minus e raised to minus j omega by 2 divided by 2j is sin omega by 2. So 2j in numerator and 2j in denominator, they cancels. Therefore, WR of e raised to j omega is sin omega n by 2 divided by sin omega by 2. The magnitude response of rectangular window for n equal to 31 is shown here, and the log magnitude response of rectangular window for n equal to 31 is shown in the second graph. For this first graph, in y-axis we take a normalized magnitude and in x-axis we take a normalized frequency. For getting this log magnitude response, in y-axis we take a normalized magnitude in dB and in x-axis we take a normalized frequency. The spectrum has two main features. They are width of the main lobe and side lobe amplitude. The main lobe width is defined as the distance between 2 points close to this omega equal to 0, where the normalized magnitude equal to 0. Here we can see that at this point normalized magnitude is 0. Here also normalized magnitude is 0. So width between these 2 points, that is the main lobe width. For this rectangular window, it is equal to 4 pi by n. And from this normalized magnitude in dB, we can see that first side lobe maximum amplitude is minus 13 dB. The magnitude response of low pass FIR filter designed using rectangular window for n equal to 31 is like this. and a log magnitude response of low pass FIR filter designed using rectangular window for n equal to 31 is like this. Here this is the pass band and this is the stop band. And pass band to stop band transition, it is gradual. But the dotted line in this graph shows the ideal case. In ideal case, there is a sudden transition, but here it is gradual transition. And in ideal case, pass band, the magnitude is constant, but here we can see the oscillations in this pass band. And in stop band, in ideal case, the magnitude is 0, but here it is not 0. Here we can see number of oscillations in the stop band. The non-zero response in stop band is called leakage. The width of the transition region is related to the width of the main lobe WR of e raised to j omega. Since the main lobe width is equal to 4 pi by n, the size of this transition region can be reduced to any desired size by increasing the number n. The increase in n also increases the number of computations. Since the side lobes of WR of e raised to j omega extend over a wide frequency range, the large magnitude components in HD of e raised to j omega become smeared over a wide range of frequencies. In the pass band, the side lobe effects appear both as overshoots and undershoots to the desired response. In the stop band, these effects appear as non-zero response. The side lobe effects do not diminish significantly but remain almost constant as the duration of rectangular window is increased. It is observed that whatever be the number of elements of HD of n included in H of n, the magnitude of the overshoot and the leakage will not change significantly. But we can change this using another types of windows. Next we consider the barlet or triangular window. The triangular window has tapered sequence from the middle on either sides. The endpoint triangular window Wt of n is defined as Wt of n equal to 1 minus 2 modulus n divided by n minus 1 for minus n minus 1 by 2 less than or equal to n less than or equal to plus n minus 1 by 2, and it is equal to 0 for other values of n. We can use this equation for odd values of n. For odd and even values of n, general equation is Wt of n equal to 1 minus 2 modulus of small n minus capital N minus 1 divided by 2 divided by n minus 1 for n equal to 0 to n minus 1, and Wt of n equal to 0 for other values of n. For n equal to 31, by plotting Wt of n versus n, we get a sequence like this. This sequence is triangular window sequence. By taking the Fourier transform of Wt of n, we get the frequency response of triangular window. Therefore, the frequency response Wt of e raised to j omega is equal to sin omega n minus 1 by 4 divided by sin omega by 2 whole raised to 2. Magnitude response of triangular window is like this. Here we plot the normalized magnitude versus normalized frequency. And this is the main lobe. And the main lobe width, we can see that it is equal to 8 pi by n. Main lobe width is twice that of rectangular window having the same duration. Log magnitude response of triangular window is like this. Here we plot the normalized magnitude in dB in y-axis and a normalized frequency in x-axis. We can see that this first side lobe amplitude is minus 25 dB here. The triangular window produces a smoother magnitude response. But the transition from pass band to stop band is not as steep as that of the rectangular window. Here we know that the main lobe width is double as that of the rectangular window. And in stopband, the response is smoother, but the attenuation is less than that produced by the rectangular window. Because of these two, the triangular window is not usually a good choice. In next class, we will study Hanning window, Hamming window, and Blackman window.